Morning. I hope everyone can hear me. Okay, today we're going to look at the next part of our module number 5, which is photo detectors. And for today's lecture, we are trying to understand the working of modulated photo barrier diode, Schottkky barrier diode, and also understand the concepts of wavelength selective detection and also working of the microgravity photodiodes. So this lecture is completely related to photodiodes. We are going to look at different types of photodiodes. Okay. So the first one is modulated barrier photodiode. It's actually a variation of something called as a Schottkky diode. So I'm not sure whether you know the concept of Schottkky diode. So normally in your diodes, you always have P and N junctions. Instead, in Schottkky diode, you have a metal and an N-type material, which you can bias. Okay. And here in normal PN junctions, the charge carriers are both electrons and holes. But in a Schottkky diode, you have the charge carriers either electrons or holes. Okay. And the metal will have some free electrons. Now, when you increase the field or increase the temperature, more and more electrons will be free, because of which there will be movement of charge. The N-type material, because of the applied field, creates electron hole pairs, and the electrons will move along the metal towards the bias. Now, this is simple working of Schottkky diode. Modulated barrier diodes is actually a version of Schottkky diode. So in this case, we are not using any kind of a metal, but instead we are having a layer whose thickness and the doping is so chosen that it is fully depleted at zero bias. So normally in a normal PN junction, you will have a small junction here, which is called as a depletion region. There will be P and N. Now in this depletion region, it is called as you will not be having any kind of charge carriers. It will have an electric field across this depletion region. Okay. Now, even if you make another layer in between in such a way that, let's say you have another layer here with some kind of, let's say, N plus or something. Now, so basically you have three junctions here. In two of the junctions, sorry, you will have two junctions here. In both these two junctions, you will have the depletion layer. Okay. Now, it might be possible that the complete middle layer will not be depleted. There will be some portion of this layer, which is this, which will not be depleted. And there will be, you can have that is a semiconductor where you will have the holes and electrons, etc., etc. The depletion layer will not have any charge carriers. Now, if I make a semiconductor in which the depletion layer or the central layer is completely depleted, that is what is shown here. You have a material in which there is a small P plus region, and there is an N plus and N minus region at the both of the ends. Because of this construction, the layer P plus is completely depleted. Okay, there won't be any charge carriers. So there is always an electric field associated with this layer. So even with zero bias, even if you are not connecting anything to this circuit, there will be a completely depleted layer. Okay, so the charge carriers, let's say a photon is incident on N plus or N minus, it will create plus and minus in whichever end it has incident. Now, if you apply a bias, let's say a reverse bias here, now because of this reverse bias, the charge carrier should move according to the biasing scheme. Now, because of this potential, there is a big potential here. Now, by applying a reverse bias, whatever potential was there before applying the bias, it will be lowered. That is what is shown in this figure. Okay. So at zero bias, this is the barrier it needs, the charge carriers needs to jump over to cross the depletion layer. So if you apply higher potential, the charge carriers will get enough energy to cross the barrier. But if you apply a reverse bias potential, now the barrier will lower itself. See, this is up to this and this is up to this. So there's a lowering of the barrier, because of which the charge carriers can cross the barrier without much of an energy. Okay, this is something called as a modulated barrier diode. So because by applying the bias, you are modulating the barrier. You are changing the barrier height. That is why it is called as modulated barrier diode. So if you want to detect any photocurrent of any particular wavelength, let's say I want to detect a photocurrent of wavelength lambda, you apply the bias in such a way that only those kind of lambda wavelength, when it is incident on the device, can produce electron and hole pairs which can jump over this barrier. This is called as modulated barrier diode. The barrier height can be modified by varying the doping of the layer. Okay, so instead of doing a different kinds of biasing, if you change this doping, P plus doping, to a different one, the barrier height can be changed. There is a significant barrier lowering with reverse bias. So when you apply a reverse bias, you see that when you apply forward bias, you see that the barrier has moved higher. When you apply a reverse bias, the barrier has moved lower. It is known as modulated barrier photodiode because of the barrier modulation possibilities. So whatever this barrier is here, which is created because of the P plus, you can change the barrier height or the depletion layer width by applying different biasing. And this is also called as camel diode because you see there's a hump because of this barrier. There's a hump like this. This is called as a camel diode. Now, just to give an example, this is a heterojunction N-P plus N gallium arsenide, aluminum gallium arsenide material. There's an aluminum gallium arsenide source, which we call it as a source, just for sake of differentiating. And there is a gallium arsenide drain. And there is a small barrier because of another gallium arsenide. So this is a P plus layer. These are all N layers. Now the gallium arsenide barrier layer is so thin so that none of the photons which is incident on that layer will be absorbed. So the photons will be incident in the left side to the aluminum gallium arsenide source. Now the aluminum gallium arsenide source have a huge potential barrier or huge band gap, because of which if you incident a photon of energy or a frequency which is less than that of this band gap energy, it will not get absorbed. Now the photon will pass across this aluminum arsenide source and reach the barrier. Now the barrier thickness is very less. Okay, this thickness is very, very small. And at this thickness, the photon cannot be absorbed. So it crosses the barrier and reaches the drain. Now in the drain, you have a gallium arsenide drain. Now the photon incident will be in such a way that the electron in the electron hole pair can be created in the gallium arsenide drain because the photon will be absorbed in the gallium arsenide drain. Now once the photon absorbed, it will create a hole and an electron. Okay, so even if there is you can get a depletion layer here also, a small depletion layer which is shown like this. This is that depletion layer. Okay, in this junction. Now in this junction, you can create an electron hole pair. The electron will move down the hill on that depletion layer, down the hill, because you have some kind of a potential in this depletion layer. And any kind of potential in a semiconductor will tilt the band diagram, and that is what is shown in this here. So the depletion layer electron will move down the barrier, move to the conduction band of gallium arsenide, and since there will be some kind of a biasing applied at the end, the electron will move out of the to the circuit. So this will create a photocurrent. Now the hole will move in the opposite direction of the electric field. So in the same direction of electric field, which is towards up direction, it will be collected in the gallium arsenide barrier. So basically in this barrier, it will be collected here, and it can move down the hill by appropriate energy and can move out of the circuit, out to the external circuit. Okay, so this movement where the hole which is at the top of this gallium arsenide barrier, if it needs to move down, then basically it needs some energy to move down, because electron needs energy to move up, while the holes needs energy to move down, because energy of the hole is converted by moving down. So it will move down by appropriate energy and goes out of the circuit. And this is a normal heterojunction in NP plus N gallium arsenide, aluminum gallium arsenide. Okay. So the thing here is the photon will be absorbed by the gallium arsenide drain, not by aluminum gallium arsenide source or gallium arsenide barrier. First thing, aluminum gallium arsenide source is of higher band gap, because of which it will not be absorbed, and gallium arsenide layer is of very thin, because of which the photon will not be absorbed. Okay, so this is a modulated barrier photodiode. Now, in the modulated barrier photodiode, you can create another structure in which, along with this P plus, you can have two intrinsic region at the two ends of P plus. Basically, the P plus region is sandwiched between two intrinsic regions, and the rest of the regions are same, N plus, and there is another N plus. So if you look at the band diagram, the working is same. At zero bias, you have some kind of a higher potential, or there is a potential barrier which needs to be crossed. And when you reverse bias, the barrier will reduce. And when you forward bias, the barrier will increase. Okay, so the P plus region is fully depleted, and the negative space charge of the ionized acceptors is balanced by the positive space charge of the I regions. Okay, so whenever you say you create a barrier, basically what happens is, or when you say you create a depletion region, basically whatever it happens is there are ionized charges at both ends of the junction. Okay, and the balancing of this junction is done using the intrinsic layers. The working of this diode is exactly same as that of our modulated barrier photodiode. There is no difference, but instead you have some kind of a balancing mechanism so that there won't be, at zero bias, there won't be extra charge. Okay. Next kind of photodiode is a metal semiconductor Schottkky barrier, or metal semiconductor photodiodes, or Schottkky barrier photodiode. Now, this Schottkky diode, we have already seen that in the first slide, that there is a metal and there is an N-type material, and you apply a bias. Okay, now the charge carriers are electrons. The metal will have free electrons. When you apply higher voltage, there will be more number of free electrons. Okay, and to create extra amount of free electrons, you need to apply some kind of extra potential. This is called as ionization potential, where your metal you are trying to ionize. Okay, that will come in the later slides. Okay, so the charge carriers are electrons in both metal and N-type, and these electrons will be moving across the junction, across the external circuit to create the photocurrent. Now, if you incident a light, it can create electron hole pairs in N-type material, of which the electrons will move out of the junction towards the metal and outside the inner circuit. This is the basic Schottky barrier diode working. But the advantage of this is there is only one majority carrier device. That is, you are using only electrons. It is very fast because of which it will have high bandwidth, and it is operated on reverse bias. Now, why it is having high bandwidth is because the reverse recovery time of Schottky barrier diode is very less. Now, reverse recovery is basically a property of any kind of PN junction, where once the electric field is applied and the carrier starts moving, if you switch off the applied bias, the diode will take some amount of time to come back to its original state where there are no charge carriers or the charge carriers are equal. Now that state depends on how much holes and how much electrons has it produced. Now in this case, since there are no extra holes produced, the electrons are the charge carriers, it can readily come back to its original position or original equilibrium position. This is called as reverse recovery. Now, as the reverse recovery time is high in normal PN junction diode, it cannot adapt to the fast changing photons or fast changing electric field, while this Schottky barrier diode can adapt to it. Okay. Now this is typical Schottky barrier diode. So in this Schottky barrier diode, the basic construction consists of there is an N plus, there's a semi-insulating substrate, it can be any of the substrates, there's an N plus layer, there is an N minus layer, and there is a metal layer. So this metal and N plus N minus is the one which actually constitutes the Schottky barrier diode. And there is a anti-reflection coating here and here. Okay, there's a contact to which you can apply the potential, which is this and this. And there is a silicon dioxide layer, small layer here. Okay, now the metal layer is semi-transparent, means that the metal layer will allow the photon to pass through it, so that this can be incident on, it get incident on this N minus layer to create the electron hole pair. Now, once the electron hole pair is created, after applying this reverse bias potential, the working is similar to that of other photodiodes, except that the electron from this N minus layer will move across the metal, and the metal will also have some good amount of electrons created because of the applied potential, which move out to the contacts. And this will create a photocurrent. Okay. So this shape where you have this one like this is called as a mesa shape. It's a mesa shape with an N plus substrate layer, an N minus absorbing layer, and a thin layer of metal deposited over it. The area of the diode is made to be 10 raised to minus 3 to 10 raised to minus 5 centimeter square. A thin dielectric anti-reflection coating is deposited on the metal, and larger top contact pads are deposited through the openings in the same dielectric. And the substrate is semi-insulating. So this is basically the construction of the Schottky barrier photodiode. There's a mesa shaped N plus substrate layer, there's a semi-transparent metal, there's an absorbing N minus layer, and there is an N plus substrate layer. Okay, so the water photon is incident, will pass through the metal, will get absorbed in N minus layer, it will create an electron hole pair, the electron will pass through the metal to the contact, creating a photocurrent. Okay, and the advantage, as I said earlier, is it is very fast, the diode, and it has higher bandwidth. Now, the full depletion of absorption region, even at low reverse bias, and both electrons and holes travel at their saturation velocity. Okay, so this N minus layer will have some kind of a complete depletion layer. Okay, where whenever an electron is created or the charge carrier is created, it is immediately swept to the other side, so that you will have a faster current. Now, there are two modes of operation for this diode. Why there are two modes is because there is a metal N minus contact. Okay, so there is something called as the metal needs, similar to we have band gap. In metals also we need to have some kind of a function called as work function. That work function is basically, you can say that the amount of energy required uh, to be supplied to a metal to create a free electron. You can say something like that. It's a work function. So when the photon is incident on the metal, if the photon has enough energy to create that free electron, then those electrons can also contribute to the photocurrent. Okay, so the mode 1 is the mode in which the photon energy is less than the band gap energy of n minus region, but is greater than the work function of the metal. That means the photon incident can create an extra free electron in the metal, but cannot create an electron hole pair in the semiconductor n minus region. Why? Because the energy of that photon is less than Eg. So once it creates that extra electron in metal, it can move to the contact and create a photocurrent. So that is what is here. So at smaller values of photon energy, such that the photon energy is less than Eg and greater than work function, electrons photoexcited in the metal can surmount the barrier by thermionic emission, transit across the semiconductor, and can be connected at the ohmic contact. So this is what I have explained. But this is not the desired mode, as thermionic emission process can be. Thermionic emission means some kind of an emission because of the temperature. Now, this is very slow. So this mode we are not going to use. What we are going to use is the mode in which the photon energy is greater than that of the band gap energy. So photons are absorbed in the semiconductor, provided that the metal layer is semi-transparent. Electron hole pairs that are created move in opposite direction with their respective saturation velocities and are collected. This is the most effective mode. So this is what we have explained. So if the metal is transparent, the photons can cross the metal, reach the n minus region, create electron hole pairs, and the pairs can move to the corresponding ohmic contacts to create a photocurrent. And this is the mode that we use in Schottkky barrier photodiode. So there is another option. So instead of a metal, what you can do is you can put a low band gap semiconductor. Okay, that means the metal layer that we have seen here, which is this one, you don't want to put as a metal layer. Instead, you just put as a semiconductor which of low band gap, because metal usually the band gap is there won't be any band gap. But if you put a semiconductor of very low band gap, it acts similar to that of a metal. With a small amount of energy, you can create the electron hole pair. Now, what is the advantage of this? So the entire diode structure can be erased by one step epitaxy. Okay, so in the previous diagram, with a metal is totally a different metal. So if you want to create the structure, you need to have more number of processes. But if instead, if you have a semiconductor instead of a metal, then you can do it in a very faster time. And making contact to the low band gap entire semiconductor is rather simple. So you create a contact here, which is this one. Now creating the contact in low band gap semiconductor is very easy, while that of in a metal is very tough. Okay, so you can have this method also. So those are the two photodiodes that we have seen. But if you look at those two scenarios, so depending on the band gap, you can dictate any kind of wavelength. So any wavelength above some particular value can be detected, because then or below some particular value can be detected, because all those photons will have enough energy to excite electrons to the higher band gap, higher conduction band. So what if we want to detect only a particular wavelength? What can we do? So this is called as wavelength selective detection. So it means that you should be able to detect only a one particular wavelength. So it is necessary to be able to selectively detect the information coming in at one frequency or wavelength when there is information coming in simultaneously at other wavelengths. So you have one wavelength information. Let's say in optical communication, you might be sending information at different wavelengths. Now I want to detect each and every wavelength separately. How can we do that? Techniques to overcome this difficulty include use of tuned filters and the use of coherent detection scheme. This we can use. There are something called a tuned filter using which and some detection scheme using which you can uh, do wavelength selective detection. While these approaches are important and feasible, systems designed with ultimately benefit from the use of detectors which display wavelength selectivity. So instead of using this extra component of tone filters and coherent detection schemes, what if we can create a photo detector which itself will detect a separate wavelength within the hundreds of wavelengths, and that we are going to see. So here the basic thing is the quantum confined Stark effect. So if multiple quantum values incorporated in the I region of PIN diode and a reverse bias is applied, then the exciton peaks move to the lower energies. This we have seen, this is called as quantum confined Stark effect. We know that when you have multiple quantum wells and reverse bias is applied, then the band gap will reduce, which means the absorption of the wavelength will be of the lower side or sort of the higher side, which means it is mostly of the redshift, red wavelengths. This phenomena was described as the quantum confined Stark effect and arises mainly due to drastic modification of the electron and hole wave functions in the well region. This is all we have seen. At very low values of bias, the photocurrent is mainly due to the recombination of photogenerated electrons and holes in the wells. As the bias is increased, the current is due to the tunneling of photogenerated carriers out of the wells and their transit across the multi-quantum well region and eventual correction. So this also we have seen in the uh, last lecture where we say that as you increase the bias, then more amount of tunneling will be taking place, because of which the photogenerator carriers will transit across the junction and creates a photocurrent. Okay, I think that slide is same as the previous. So this is the graph which explains a wavelength selective detection. So if you look at this graph, you see that whatever is specified here is actually different wavelengths. So these are wavelengths. Okay, so these are the reverse bias voltage that you are applying. So if you see, let's take a one voltage here. Let's take 10 volt. So for 10 volt, if your current is something around here, which is let's say 2.5 amps, microamps, then you say that the corresponding wavelength incident is 8640 Armstrong. Now, at the same reverse bias voltage, if the current is approximately 3 microamps, then you say that the wavelength incident is 8630 amps. At 10 volt, if the current is, let's say, 5 microamps, then the wavelength incident is 8620 Armstrong. So by setting a reverse bias voltage and by measuring the photocurrent, by looking at the photocurrent, you can say what is the type of the wavelength that is incident. Now this is basically for this kind of structure. This is basically for gallium aluminum arsenide with aluminum gallium arsenide substrate and of the ratio 0.3 by 0.7. So in this material, by setting a reverse bias voltage and looking at the photocurrent, you can say what is the corresponding wavelength which is being incident. Okay, so the value of photocurrent is distinct for different wavelengths. A change in the input wavelength of 100 angstrom produces a change in the output voltage of 10 volt. Okay, so this is around, you see, 8640. Okay, and this is 8580. So the difference between these two voltages is around 10 volt, and the wavelength that can be detected between these two voltages has a difference of 100 angstrom. That's a very huge difference. Okay, but here the only problem is, but only one particular wavelength can be detected. Now, when you have this optical communication, lot of wavelengths will be coming transmitted, and you won't detect all the wavelengths. But here, using this kind of material, you will be able to detect only one particular wavelength. But how is it possible to detect all those possible wavelengths? And that is done by another structure. So in this structure, you see that you have two uh, PN diodes with a multiple quantum well, and they are connected to reverse bias. But the reverse bias voltage have a relation. So if this is V, this is V plus delta V. So this is 10. This will be 10 plus 0.1 volt, something like that. Okay, and you see the light incident has sum of lot of wavelengths. So this means that this is equal to lambda 1 plus lambda 2 plus up to lambda n. Similarly, light incident here has lambda 1 plus lambda 2 plus up to lambda. So lot of wavelengths are incident on this structure. Now, how this is found out is we are going to look at delta IPH by delta lambda. This is what you are going to look. So delta IPH is the difference of the photocurrents between these two quantum well structures. Sorry, this is not delta lambda, this is delta V. Okay, and you're taking the ratio of the difference of photocurrents to the difference of reverse bias voltage applied. Now you see that it is plotted here. So for any V versus delta IPH by delta V, it is plotted. And the plot is for four different wavelengths. That is the wavelengths that corresponds to the plot is like 8350, 8370, 8410, and 8430. Let's say I want to detect wavelength corresponding to 8350. Okay, this is the wavelength that I am going to detect. So what I do is I will measure, I'll take any two combinations. Okay, so this can be, so if wavelength is present, I say it is an on state. If the wavelength is absent, I say it is an off state. Okay, so I can take, let's say this is lambda, this is lambda, this is lambda 1, lambda 2, lambda 3. So if I take any two combinations, lambda and lambda 1, I can have on, 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 off, off, on, off, off. Okay, so you take any two lambda and you found out all these states. Okay, and you find out at each of the state what is the ratio delta I by delta V. Okay, similarly you take the next one, lambda and lambda 2. So lambda is the wavelength that you want to detect. So you take the combination of lambda, lambda 1, lambda, lambda 2, lambda, lambda 3. All these combinations you take. Okay, sorry, this is up to lambda 3 only. So you take all those combinations and you sum it up. Means uh, you take the value of delta I by delta V and you plot for different values of reverse bias what is the corresponding graph. So that is being plotted here. Okay, and then you take only lambda, you find out what is delta IPS by V. That is what is plotted here. This actually a bold line which might not be available shown, which might not be visible for you. So that is what it's here. Now you can see that for any particular reverse voltage, depending on the corresponding values of delta IPS by delta V, if the value is high, that means the voltage, the wavelength that is being detected is lambda or lambda 1 or lambda 2 or lambda 3. Okay, so By this way, you can detect the different wavelengths from a single wavelength. Okay, this is called as wavelength selective detection. Now, the last topic of this lecture is microcavity photodiodes. Now, why do we want to use photodiodes? Microcavity photodiodes is, see, if you want to have high quantum efficiency, means for all the incident photons, there's a huge current created, or then what you want to do is that you want to make your region or the region in which it is exposed to the light should be as thick as possible. But when you make the region thick, the problem is the electrons will take good amount of transit time to cross the barrier, and this will reduce the bandwidth. So always there is a trade-off between quantum efficiency and bandwidth. So there is a fundamental trade-off between quantum efficiency and bandwidth of a photodiode. A large value of efficiency parameter necessitates the use of thick absorption region. So if you have a thick absorption region, more photons can be incident, more light will be absorbed, and more current will be produced. While a larger bandwidth dictates the need for a thin absorption region. Lesser the absorption region, faster the electrons can cross the barrier, and faster will be the response, and higher will be the bandwidth. So the thickness of the absorption region is always a compromise, whether you want to have high quantum efficiency or whether you want to have high bandwidth. Such a trade-off can be avoided by using a microcavity photodiodes. So using microcavity photodiodes, you don't want to look at all these things. So this is a microcavity photodiode. So what all things are there? A thin, low bandgap absorption region is placed in the middle of a resonant cavity formed by heavily doped wider bandgap regions and reflecting mirrors. So this is your absorption region, indium gallium arsenide absorption region. Now it is placed at sandwiched between two regions, which actually forms something called a resonant cavity. There's a resonance which will be formed, and they are of wider bandgap. So the photon which is incident from here will directly go to the absorption region. It will not be absorbed in p indium phosphide or n indium phosphide because they are of wider bandgap. And there are some reflecting layers. Okay, the bottom reflecting mirror is formed by a distributed bag reflector, while the top mirror can be dielectric film or stack. So this is actually something called as a Bragg reflector. So whatever light is incident will undergo some kind of a reflection. Similarly, there is a dielectric stack which is also a reflector. Now the quarter wave superlattice reflector is made up of alternate layers of high and low refractive index. Each of thickness is equal to lambda by 4. So this is actually a quarter wave lambda by 4 superlattice. Now this is made up of multiple layers, each of low and high refractiveness. So the first layer might be low, then high, then low, then high, and goes on. So you see that, you know that whenever there's a change in refractive indexes, there will be total internal reflection, and there will be bending of light. So a lot of things are there when you have this Bragg reflector. The light reflected at each interface interacts constructively at the surface. The reflection coefficient of the entire stack depends on the difference in the refractive indices and the number of periods, and can be made quite large. Now this light, when it gets through this region, absorbs here. Now the same light can move across the Bragg reflector, can create some kind of a total internal reflection, and only those light which will survive, which interferes within each other after reflection, has a constructive interference. Okay, so the resonance, so the light which is coming here will travel back and forth, and only those light which have a constructive interference between the forward traveling and backward traveling light can survive in this cavity, and those light which survive in this cavity will produce something called as a resonance, means there will be a huge gain. So a resonance is built up in the indium phosphide cavity at those frequency components of the incoming light for which the round trip phase shift is a multiple of 2 pi. So the light coming here and reflecting back, if there's a phase shift of 2 pi at any point, then there will be a resonance, which means the light will survive in that corresponding cavity. At resonance, frequency of the incoming light is reflected at two mirrors and the round trip path length is greatly increased. So at resonance, you are basically creating a round trip path in which you are increasing the resonance. However, the transit length remains same small as the photogenerated carriers only have to traverse the thickness of absorption region to be collected. But the transit time will remain same because once the photon is incident here, the electron hole pair will be created and it needs to cross only this part. It need not cross the complete this part. So the transit time of this electron will remain the same, but the quantum efficiency will also increase because you are creating a resonance cavity inside this diode, because of which the quantum efficiency more light will be absorbed to create higher current. So microcavity photodiodes therefore makes a simultaneous achievement of large bandwidth and high quantum efficiency possible. Thus, you can have large bandwidth and high quantum efficiency. So high quantum efficiency is achieved by resonance in the circuit, wherein which you can absorb, wherein which there will be a resonant wave inside the circuit creating more absorption and creating higher gain. And even though the photon absorbed, since the photon absorbed need not travel the complete photodiode length, instead it needs to travel only a small absorption region length, the transit time of the electrons will be less, which will increase the bandwidth. Okay, yeah. So that's about microcavity photodiodes, right? So I think we have covered some good amount. Right? So just go through this and let me know if you have any doubts. Now, I'll try to see if I can give notes. I'm not committing on that. Let me see if I have